Okay, so I kind of went through an explanation of why this worked, right? Okay, a sub 1 is whatever the first term of the sequence is, and then you're adding the common difference one less time than whatever term you want to get to. All right, so it's pretty easy. Now, I'll give you a little shortcut method too. Okay, some of you will like this, some of you will just use this every single time. Okay, now everyone's going to have to use this in a way for different types of problems, so everyone's going to have to know this. But I want to teach you a little shortcut here to do this one. An arithmetic sequence, like I said, is a line, right? What equation do you think of when you think of an equation for a line? Y equals mx plus b, right? M is your slope, and b is your y-intercept, okay, where it crosses the y-axis, right? Okay, well look at this sequence of numbers. What is my rate of change? 5, so guess what my slope's going to be? 5, which matches, right? Okay, like y equals mx plus b, okay? So 5 is your slope, okay? Now, the b value, you guys said, is the y-intercept, right? So the y-intercept, here's my y-axis, okay? What is the x value on the y-axis? 0, right? Everywhere on the y-axis, my x value is 0, correct?
Yes.
Okay. So if you can kind of figure out the 0th term of this sequence, you will be figuring out your b value. If you can figure out the 0th term, doesn't really essentially exist. But here's my first term, here's my second term, here's my third term, here's my fourth term. Okay, well let's work backwards. Fourth term, third term, second term, first term. What would my 0th term have been if there was a 0th term? -4, right? Well, look at that. There's your y-intercept. Okay, that's pretty quick. All right. Same thing over here with this one, the one I had you guys do. Okay. We know that this simplifies to 3n plus 9 after we distribute and everything. Okay. Well, if you look, why is my slope 3? Because I'm adding 3 every time. And my y-intercept is 9, because that would have been the 0th term. That would have been the term that happened right before the 12. Okay? So that's kind of a little shortcut you can definitely use to write a rule, but again, this only works for an arithmetic sequence where they're adding the same number over and over and over again.
What if they're multiplying?
That's where I'm going next, Kate. All right?
Then we have to use that one.
Nope, there's a different rule for it.
Oh.
Very similar. It's just with multiplying instead of adding.
Wouldn't it just be exponential?
Yeah, yep, exactly. Very good.
Sure, buddy.
All right. So, that was for an arithmetic sequence. This was just a problem I picked out of the textbook. You can probably put it in your notes as a good example to refer to. Okay? But this one, 1, 2, 4, 8. What's my pattern? Multiplying this time by 2 over and over and over and over again. Okay? Anytime you're multiplying by the same number over and over and over again, that is not an arithmetic sequence. That is called a geometric sequence. Okay? A geometric sequence, when you're multiplying by the same number over and over and over again. Okay? Now, what if the pattern was dividing by 5 over and over and over again? Is that geometric?
Yeah.
Because what number are you multiplying by over and over and over again if the pattern is dividing by 5?
-5.
1/5. Yep, multiplying by 1/5. Okay? Because what's 25 times 1/5? 5. Be just like dividing by 5, right? Okay? So multiplying and dividing patterns, this geometric rule will work. Okay? So a geometric sequence is a lot like Isaac said, an exponential equation. Okay? An exponential equation. You're multiplying by the same number over and over and over again. The rule is very similar. You know how the rule for arithmetic was the first term plus the difference in -1 times? First term times the ratio in -1 times. And the ratio is whatever number you're multiplying by over and over and over again. Okay? That's what I wrote over here, the common ratio. The common ratio is whatever number you're multiplying by over and over and over again. So in this case, the pattern is we're multiplying by 2 over and over and over again. Okay? So a sub n equals a sub 1, that's my first term, so 1, times my common ratio, which I'm multiplying by 2 each time, so 2 to the n minus 1 power. Okay? And that's it. There's nothing to simplify here. I guess you could not write the 1, because you don't have to write the 1 there. You could just say a sub n equals 2 to the n minus 1 power. That would work. But now, why is writing this rule helpful? What can you do with this rule? Plug a number in for n so you can figure out the 20th term, the 30th term, the 50th term without actually having to write them all out. Okay?
Is there one of your fancy shortcuts for this one too?
Okay. It relates back to your exponential equation, y equals a times b raised to the x power. It's not quite like that because it is going to have this n minus 1 up here. But if you remember exponential equations, y equals a times b raised to the x. A represents your starting amount. B represented the number we multiplied by over and over and over again. So it's really very much like that. It's just that isn't remembered as well as y equals mx plus b, so I don't refer to it, but it is. It's basically the same. You do need the n minus 1 there, though. Okay? So, that's a geometric sequence. Alright? Most of your problems will be either arithmetic sequences or geometric sequences. Okay? Most of them, and especially today. Alright? There are some other ones that you could see. Like if you see 1, 4, 9, 16, 25, that's definitely not arithmetic because they're not adding the same number over and over again. It's definitely not geometric because they're not multiplying by the same number over and over again. But what's special about these numbers? They're perfect squares, right? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, so my rule is n squared. Okay? Yeah, that'd be it. Because if you plug in a 1 for n, you get 1. Plug in a 2, you get 4. Plug in a 3, you get 9, so it works. Okay? Some people say, well, you're adding 3, then you're adding 5, then you're adding 7, then you're adding 9. Yeah, that's true. Very true. Hard to write a rule, though, where you're not adding the same number over and over again. Okay? But if you ever see that pattern, add 3, 5, 7, 9. Like in this one. Add 3, 5, 7, 9. Okay? Anytime you see that pattern start to happen, you know you're going to have an n squared probably in your rule somewhere. Okay, but this one would be n squared plus 5. Because 1 squared is only 1. I need it to equal 6. So 1 squared plus 5 would equal 6. 2 squared plus 5 would equal 9. 3 squared plus 5 would equal 14. So this would be the rule for this one. So sometimes you might see rules that have n squareds in them too. So just kind of be aware of that. Be looking for those perfect squares. Okay. They do get a little more complicated than those first few that we've done there. Okay? But they're not bad at all. Once you get used to using these rules, this is really pretty simple. Okay? Alright, so here's a more complex problem. I know the 15th term in the sequence is 42. Okay? And I know my common difference is negative 3. My goal is to find the 100th term of that sequence. Okay? Well, could you write out the next 85 terms?
Yeah.
I suppose you could. Alright, you have fun with that. Alright. I would not do that. But you could write out the next 85 terms. Alright? Our goal is to find the 100th term. Well, if we want to find the 100th term, wouldn't it just be helpful to have the rule for the sequence? Because then all you got to do is plug in 100 to find your 100th term. Okay? So, But in order to write the rule, I need to know the first term. So I guess if you wanted to, could you find the 14 terms that came before this one to find your first term? Yeah, I suppose you could. But again, I still think that would kind of suck too. Alright? So I would just use this equation to help me find the first term. I know that my 15th term is 42, so that means if I plug in a 15 for n, I'm getting 42 for an answer, right? You guys follow me on that? If I plug in 15 for n, I'm getting 42 for an answer. So I'd write 42 equals a sub 1 plus my common difference was negative 3, and then what number did I plug 15 in for n? 15. Okay? So I would just write out this rule and then solve for a sub 1. Because once you have a sub 1, then writing the rule is simple and you can finish the problem. 15 minus 1, that's 14. Negative 3 times 14 would be negative 42. So a sub 1 plus a negative 42, or in other words, a sub 1 minus 42. Add 42 to both sides and you get 84 equals a sub 1. So my first term of this sequence must have been 84. Purely coincidence that it was exactly double. That was just randomness, okay? Alright. So my first term is 84. Well, now I can write my rule. Okay? A sub n equals my first term, 84, plus my common difference, so plus negative 3 times n minus 1. So a sub n equals 84 minus 3n plus 3, because a negative times a negative gives me plus 3. So a sub n equals negative 3n plus 87, or 87 minus 3n, however you want to write it. So there's my rule. Now, how do I find the 100th term? Plug in 100. What's negative 3 times 100? Negative 300 plus 87? Negative 213. Nice job. So you can do one of two things. You can just write negative 213 and circle it, or you can write a sub 100 equals negative 213. Okay, I don't care how you write it. Okay? So, any questions on that? You'll do some that are with geometric sequences like this too, where they give you like the 8th term is this, and you got to find the first term. It's very similar to this, okay? I don't know that I necessarily need to go through a problem with you, I certainly can, but I think you get the general idea. You will use this rule a ton, and this one. So I'd probably get those memorized, okay? And really, to memorize them, I think if you just do the practice, you'll have them down pretty good. Okay? Just be aware of it, so if you get to a practice problem where you're not recognizing the pattern, know that it could be an n squared in there. Alright, so
Not yet. I gotta get their homework.
you guys have done this one. I've checked you off for this one, those of you that are here. Alright? Those of you not here watching the video, you do need to do this. Okay?
Let's see.
These two. See how much of that you can get done before you go. A lot of people got the first one done before they left class. Some people got a decent start onto this one before they left class too. Okay? These two. You don't need to do this one yet. I teach this stuff tomorrow. Alright? So, check your answers. Whatever you get done, you can turn in. We'll call it good.
Bye. Cut.
So if I get one